Hello everyone, I'm Mojtaba and welcome to another episode of A Sip of Chemistry. Glass science has been advanced by many brilliant researchers whose work deepens our knowledge, understanding, and insight into this fascinating field. Among these scientists is Professor Grant Henderson, who initially entered glass research from the perspective of a geologist. This isn't surprising because geology often involves studying magmas, silicate melts that are naturally amorphous, making them of particular interest to earth scientists. He's currently an Emeritus Professor in the Department of Earth Science at the University of Toronto. His research primarily focuses on investigating the structures of gases and melts through various spectroscopy methods, including Raman Spectroscopy and synchrotron-based techniques such as EXAFS and XANES. I found our interview an excellent opportunity to ask detailed questions about Raman spectroscopy, but our conversation wasn't limited to science. I also asked Professor Henderson about his activities beyond the lab, as well as a few fun questions. If you are interested in glass science and want to learn more about Raman spectroscopy, please stay tuned and enjoy my interview with Professor Grant Henderson. Thank you so much, Professor. Thank you for making actually this time for having this interview. I'm excited about it, and please tell more about yourself. Where did you go to school and university? Where and when?
Okay, so I am originally from New Zealand. And I went to the University of Auckland in 1974 to do I did a BSc and MSc at or bachelor's and masters at the University of Auckland. There was no such thing as joint degrees in those days, but I did everything jointly between chemistry and geology. So even for the masters, I asked to substitute some of the geology courses with chemistry courses, which they allowed me to do. That had not been done before. But anyway, I did a BSc and MSc there. I didn't do what I originally intended to do, which was to do a PhD in virology. And I got put off working on biological stuff in first year. My first year courses in botany and zoology for various reasons. Mostly I couldn't draw, so I could dissect things really well, but I couldn't draw very well. And I kept getting low marks because of my drawing, and I thought, to hell with this, and I really enjoyed geology, so I ended up taking the BSc officially is in geology, and my master's is officially in geology. Although, as I said, it was I did all the chemistry courses. I always took extra courses throughout my BSc and MSc. And then at the end of my master's, I got a postgraduate fellowship to go do a PhD, but they wouldn't let me take it overseas. And I was encouraged to apply for universities overseas. So, and again, at that time, there was very little information about how to go and do a PhD somewhere else. And the place I really wanted to go to was MIT, and I did not apply to MIT because of the massive fees and things. I didn't understand that you could get fee waivers and scholarships to cover all this. And the funny thing was, I actually got to know the person at MIT who I wanted to work with originally. I got to know him quite well a few years later, and he just said to me I was an idiot for not applying because he would have accepted me straight away, which kind of upset me at the time. And then I applied to go to Western Ontario because there were two people there I wanted to work with. One was a guy called Bill Fife, who is a New Zealander and was a very famous geochemist. And the other guy was a guy called Mike Bancroft in chemistry, because he wrote a book on Magma spectroscopy. And all the way, my undergraduate marks are not very good. I didn't really try too hard. And, you know, you get sick of just sitting exams and stuff like that. But when I went to grad school, I really enjoyed it, and everything greatly improved. And I got interested in spectroscopy in general when I took a second-year chemistry course on various techniques. And Raman is one of the techniques I really got involved with. And that in that lab, there was a lab in that class where we did a Raman experiment, but we're using the old style mercury arc lamps and photo film, and no such thing as lasers for Raman at that. Well, they came out shortly after, but and I thought it was a fascinating technique, so I enjoyed that, and I got involved in a lot of different techniques to investigate how a particular type of mineral formed. But anyway, I ultimately applied to UWO, but I got tossed out. They wouldn't accept me, and that's because of the timing between the two academic years is somewhat different. And I did not have my graduate course marks or my master's results. So I had asked the chair of the department to send them, but he didn't do that. Instead, he turned around and offered me a load of money to stay at Auckland to do a PhD, which I kind of started for a few months, but it was not really what I wanted to do. And then a prof from Western wrote to me and said, "Where are your graduate marks?" And as soon as I sent them, I was accepted because they're all very good. And I went to Western. I ended up working on glasses. And originally, in the early 80s, there was a lot of interest, late 70s, early 80s, a lot of interest in looking at the structure of igneous melts. And the main proponent who was working on this, there were two people really. One was Bjorn Meeson, and the other was Paul McMillan at Arizona State at the time. And one of the problems is working on molten materials in the early 80s. It was very difficult. So what everybody was doing was quenching melts to form glasses. And that's how all of the geology community got involved in glass research and so forth. And I got wrapped up in it because I started off looking at iron in melts. And there's a lot of issues dealing with things like iron, because you've got multiple oxidation states and multiple coordination environments. And quenching the iron glasses is a problem. It's not easy to do. And I had a bit of a disagreement with my supervisor at that time, and I stopped talking to him. And one of the things that happened was that because I was having trouble I needed to really look at the iron glasses in different oxidation states, and I was just quenching them down from a melt. And we did do some work on X-ray diffraction of iron glasses, and that also was in its infancy. And one of the things there is that I got sent all of the software that Connet and Carl were a group of people working on silica and glasses. They sent me all their software for data collection and data reduction and modeling. And I got all of the raw data from Mosey and Warren, who are a well-known couple working on SiO2. They sent me their raw data, all of it in the form of cards eventually, because you just had boxes of cards. There's no such thing as, you had to lug the cards over to the computing center. But because of the problem with the iron, I decided to switch to substituting, focus on Raman rather than X-ray scattering or diffraction. And I decided to substitute gallium for aluminum because I was looking at albite, for example. And I switched gallium for aluminum, and I switched germanium for silicon because the heavier mass of the atom should shift the Raman peaks. They kind of do, but that's not necessarily always right. And so I looked at gallium and germanium glasses, and that's eventually what I did all the work on, mainly with the iron. It was Mosbauer and X-ray scattering, and with the gallium germinates, it was Raman. And I used to go up to the University of Waterloo every weekend for months on end and run Raman spectra. And in those days, you had a photomultiplier, and there was it took an extremely long time to get a glass spectrum. It usually we'd get maybe 2 overnight, running the whole instrument overnight, because you simply didn't have the detector sensitivity like you do now with CCDs and so forth. It was a photomultiplier and things like that. And the system I was using, they weren't used to glasses. And of course, glasses always have very broad signals, and you have to open all the slits up, and you got to make sure that you can actually see these peaks that are usually in the background for crystalline materials, right? Yeah. And so took a while, but we did a lot of that. And then when I finished, there were no jobs in geology anywhere. Well, I shouldn't say that. I did get offered some things, but for personal reasons, I ended up having to stay in the Toronto area. So a friend of mine had a friend working at York University who said he was looking for a postdoc. The only problem was it was in a completely different field. So I went up to see this guy, and the only thing he asked me was, can you write computer code? And I'd had lots and lots of experience at writing Fortran. So I said, yeah, I can write computer code in Fortran. Mm-hmm. But the project was to look at particle precipitation into the outer atmosphere of Jupiter and Saturn. It was atmospheric chemistry or physics. So anyway, cut a long story short, I ended up there for almost 5 years building numerical models for, they discovered the Antarctic ozone hole in October 85. So we switched this big numerical model I was building, we switched it from outer space down to the stratosphere on Earth. And we spent a lot of time looking at the ozone hole. And I actually got more interested in hydrocarbons down near the surface and processes over tree leaf canopies and near the surface. Mm-hmm. And then one day I got a letter from somebody at the University of Manchester saying, do you want to come for a job interview? And I started to get all these interviews in geology, but of course I wasn't working in geology anymore, right? Yeah. So I had to explain that any talk I was going to give on melts was a few years old. And because I hadn't spent any time looking at it. Anyway, I eventually got this job at U of T. And that was in 1989. Not 89? Yeah, 89. And they had just developed the atomic force microscope at that time. And so I applied to get one, and my goal was to see if I could see the glass atoms in glasses, right? Yeah. And so I got heavily involved in that, but then I came up against it's the usual. Well, it's a problem when you're in geology and you're trying to publish in physics or chemistry. Okay, they think you're a second-class scientist and don't know what you're talking about because you're not a physicist or you're not a chemist. And so we did all this work with AFM, and a group of physicists basically said everything we produced was fake. It was an artifact of some process. And so it became very difficult to do any work with AFM and try and get it published in physics, like physical review letters or, various things. And by chance, I happened to run into a Russian theoretical physicist who had worked in Russia on AFM forces. So we ended up doing a lot of theoretical work on proving that what we saw was real. But the physicists still chucked it all out. And the funniest thing about 10 years ago, there was a paper by Gerhard Binnig. He's the co-inventor, won the Nobel Prize. And he published this paper in Science on the calcite cleavage plane. Well, we looked at the calcite cleavage plane in 1995, I think. And he cites us in his science paper in this thing. What he doesn't say is his results are exactly the same as ours, and we have better images. Because, and what he concluded was that one of the oxygens extends out of the cleavage plane. And that's exactly what we said. And our images are better. So as a result of that, I thought, to heck with this. So I went back to glasses. I find working on glasses very stimulating because they're very difficult to study. I think there's always things that surprise you. So intellectually, I find I'm always sort of stimulated, or was always stimulated by looking at glasses. And one of the things I find right up to this day is that there's a lot of rubbish out in the glass literature because many people that do research just do not want to accept new information or things that contradict the commonly accepted idea. In glasses, you have modifiers and formers and BOs and NBOs. Well, there's a lot more to it than that. The BOs have modifiers attached to them, just like in crystals, okay? And so a BO, it's not just a BO. There is a BO with nothing attached to it. There's a BO with one modifier attached to it. There's a BO with two modifiers attached to it. And there's a BO with up to 3 modifiers attached to it. And people completely ignore this when they describe glass structure. And then they try to interpret physical behavior based on this model that's partially correct, but not completely correct. And they hate it when you point out that maybe they've got a lot of things wrong. And I'm quite blunt at meetings, so I'll say, you guys have it wrong. And I will explain why. But they don't want to admit that maybe we're right. And all my papers take a long time to get cited. There's no interest in them for several years. And suddenly they take off because they suddenly realize, oh, they did know what they were talking about. So there you go. Does that cover enough?
Yeah, of course. Yeah. Thanks for your explanation. Actually made it easy for me just to ask more questions. You actually answered most of them. Let's talk about a book, encyclopedia book on glasses. So that's an amazing textbook. I love it. And what's your contribution to this book? You have written a chapter in this book. Would you tell more about it? This project?
Yeah, this is the one by Pascal Richet, right? Encyclopedia of Glass, parts 1 and 2.
Yeah.
Yeah, so I wrote a chapter on structural probes. It's a sort of overview of some of the common techniques you use to probe the structure of glasses.
Mm-hmm.
I didn't go into huge amounts of detail, but it enough that if you're a beginner, it's not a bad place to start. I kind of like writing review papers, and I aim them at graduate level. So in geology, I've done, you in geology or chemistry or something else?
My background is materials science and engineering, but my PhD is in chemistry.
Okay. So in geology, there's a series of magazines called Elements.
Mm-hmm.
And they consist of about 6 chapters, and each chapter is about 5 pages long. And they're aimed at general non-scientists and undergrads and grad students. And there are quite a lot of them, but there's one on glasses that we did in 95. And there's another one on thermodynamics that I did. And these things, I try to write them at a level that for the students, right?
Yeah.
And then I did, there's a thing called Reviews in Mineralogy and Geochemistry. And one of the things, if we go back to glass sciences, I find that the physicists and the material scientists and things don't read outside their fields. So there was a while back, there's a lot of interest in titanium silicate glasses, but we looked at that in the mid-90s, and nothing was new that came out on titanium silicate glasses. And the Reviews in Mineralogy and Geochemistry books, so we did one on spectroscopic methods, and we did one on geological, just recently, 2 years ago, on geological melts and glasses. And they're excellent summary chapters of different techniques, and they're easily readable. And I guess to some extent, I have a reputation for enjoying writing these things. So with the encyclopedia, now I know Pascal Richet very well, and I've spent a lot of time at IPGP where he's based. And so when he was discussing writing this encyclopedia, he asked me to write this chapter, and he asked many, many people all over the globe to write those short, relatively short chapters.
Yeah, that's I agree. That's a great book, and I read most of the chapters on the fundamental things, the theory behind glass forming abilities. I would love to ask you a few more detailed questions in glass science. You are a special, one of your expertise is Raman and XANES and EXAFS. I would love to know how these techniques could help in answering hard questions in glass science, like distinguishing between the bridging oxygen and non-bridging oxygen.
The best way to actually distinguish bridging oxygens and non-bridging oxygens is X-ray photoelectron spectroscopy. Now, a lot of people will say this is predominantly a surface technique.
Mm-hmm.
That is not entirely true. About 80% of the signal comes from some depth beneath the surface. So there's a lot of good stuff in it in XPS. But in terms of glasses, about the only thing it's good for is it'll give you the total number of bridging oxygens and the total number of non-bridging oxygens. Now, of course, there's more to the glasses than bridging oxygens and non-bridging oxygens. There's ring statistics. There's free oxygen, which people are starting to realize is there. But this is sort of like how do I say this? In the 80s, in geology, people would refer to free oxygen, which is an O2 minus. So Na2O is free oxygen, okay?
Yeah.
But NMR was developed in the 80s, and NMR, I don't do a lot of NMR. I know everybody that does do NMR. I think it's a very powerful technique, but it doesn't see everything. And in the 80s, it sure as heck didn't see anything. The more recent stuff in the really high field NMR techniques is a lot more sensitive to different things in the glass. So you can start to see things like free oxygen and different types of BOs and NBOs and things like that. In terms of glass structure in general, as I said, the diffraction techniques, they give you the overall sort of interatomic distances and angles. And you're kind of limited there unless you can somehow model it, which is not really done that much. If they do, like MD people or the modelers, they'll compare the structure factor to the I forget the term for it, but they compare it to X-ray diffraction, and X-ray diffraction is very insensitive to glass, the subtleties of glass structure. Mm-hmm. And so when the MD guys compare it to X-ray diffraction experiments, they say, look, it matches. Well, it may match generally, but it's not telling you anything about the details. So to get the details, I find that Raman is by far the most sensitive technique to that. It has a huge amount of information in the spectra. A lot of the time, you have to curve fit the results at the high frequency end. And there are massive issues with how people interpret Raman spectra, okay? Mm-hmm. Curve fitting in particular, and I'll come back to that. EXAFS and XANES, well, EXAFS gives you coordination numbers, fairly okay coordination numbers. They're averaged. You're getting the average coordination number. So if you've got five-fold, it might be you have five-fold, or it might be it's the average of 4 and 6. Mm-hmm. So it's difficult to interpret. XANES is good for light elements for the electronic structure, and it's qualitative information on oxidation state and coordination numbers. Now, NRICS, or X-ray Raman, is a relatively recent development, and that looks at the soft X-ray, the light elements, oxygen, silicon. You can't get EXAFS below silicon, okay? It doesn't work. There are interference effects. There are problems with it. But so if you're interested in oxygen in a glass, XANES is one of the few ways you can get information on the electronic state. One of the things it can do is oxygen will be, if it's bonded to different silicon coordinations, you can actually see that because there's shifts in the oxygen XANES. It's very qualitative and it's not very precise. Now, NRICS, the big advantage of that is you can get essentially the XANES spectrum of light elements at high pressures. So if you want to look at stuff at 50 GPa, you'd use X-ray Raman or non-resonant inelastic X-ray scattering. It gives you essentially it's not the XANES spectrum, but it's exactly the same as the XANES spectrum of the light elements at pressure. See, people want to know what's happening at high pressure and high temperatures, and there are always issues with high pressure, high temperature. And NRICS and X-ray Raman are kind of a nice little technique to use. In terms of just looking at the structure, I do believe Raman is the best. You get the most information out of it, but it's often misused in the sense that, for example, the high frequency part of the spectrum around 1100 wave numbers is where all the NBO Q species vibrations are. So you have Q0, Q1, Q2, Q3, Q4. Now, one of the problems with the fitting, and to some extent, I think this still goes on, you get people and they get a program like YK Fit, which is free off the internet sort of thing, and they fit their spectra and they let the program fit their spectra and they get this beautiful fit. And they never question whether that is reality. Is that really the fit? And one of the things when you fit glasses is you have to spend many, I would say, days fitting the envelope manually. Don't let the program do it, okay? You assign positions, full width, half maximum, intensities, and you fit the envelope over and over and over again, adjusting all the parameters slightly until, and you do it for one peak, okay?
Yeah.
And you get the shoulder, say, on an envelope, you get a peak there. And after several days of doing this, you'll get a feel for what the numbers are for the intensity, the position, and the full width at half maximum. Now, the full width at half maximum, we know, we published a series of papers on this where we know how broad the peaks for Q1, 2, and 3 and should be. And they're not Gaussian curves. Everybody fits Gaussian curves. They're Lorentzian. And the Q4 peaks are Gaussian. They're the only ones that are Gaussian. Everything else is Lorentzian with a Gaussian component. So you have to fit them with pseudo-voids or voids. And you have to do it over and over again. And you can see in the literature these studies where they've fit the same glass composition, but for different reasons. And so they get a different fit. That's nonsense. The fit's the fit. You fit the envelope, that's it. When you got it, that's it. You have to, unless there's some major more structural information in there telling you there's an extra peak or not, you can't keep changing the fit depending on how you're interpreting your data. I mean, that happens all the time. And they still constantly fit Gaussians. And if you fit Gaussians, you end up having to fit extra peaks that don't exist because the envelope is not fit well at the edges of the Gaussian. But if you use Lorentzian, it fits very, very well, and you don't require extra peaks. So you've got to, when you're using Raman, you've got to think about it a lot. It's a simple technique. You'll get great data, but you've got to really think about how you fit the spectra and why you're fitting them and whether or not what you're fitting is real.
Since we were talking about Raman, I would love to know how has it changed the engineering behind it. I mean, how it has developed the Raman spectroscopy within the past few decades. That's one of my favorite topics. Different techniques, how they have changed over.
Yeah, well, Raman, I mean, the big thing is the lasers. You got a variety of lasers now you can use, including infrared, like, infrared lasers in the infrared range. The big thing is the CCDs and the sensitivity of the detectors, and the ability to cut out fluorescence and so forth. And of course, you can go with pulsed lasers, which I think one area that's drastically underutilized, where they could be useful, is at high temperature. So high temperature Raman is you have a problem with black body radiation off your sample. And there was an abstract on the molten SiO2 by this, I forget his name, but it was only an extended abstract. And I called him up one day because I wanted a copy of the full abstract. I didn't have the extended abstract, and asked him if he had published anything else. And we had an interesting conversation because he said it's one of his biggest regrets is not actually publishing the paper on this because this thing's been cited dozens and dozens of times. But when you look at high temperature stuff, you got to use a chopper. So you got this black body radiation coming off your sample. And so what you have to do is you have to kind of block it out and then just open it up when you want the signal and shut it again. And there are ways to get high temperature spectra. And I mean high temperature. I don't mean using a Lincoln stage up to, say, 1,000 degrees. I mean, this guy with SO2 went to 2,000 degrees centigrade. So the sensitivity of the CCDs, I mean, when I first did Raman, it took, hours to get a single spectrum because it's very weak signals, but it takes 45, 50 seconds on a modern instrument on a glass once you set it up for looking at amorphous things, or and that's not a big deal. That's just making sure the slits are wide enough and so forth. I haven't used I've never had a Raman instrument, never been able to get one from NSERC. Okay. And these days, lots of people have them, but they're all using them just as a way to identify inclusions in meteorite samples and things like this. They're not actually, it's just an instrument like a characterization technique. They're not actually doing research with the really on Raman spectra. They're just identifying things. Yeah. And I never could get one. I wish I could have. So I used to always go to France and use one. If you want to get down to 20 wave numbers, you have to have a triple pass monochromator to spread the signal out. A single pass or a double pass, which is what most people get, is not sufficient to get down to the very low frequency peaks. And Raman imaging has become quite popular. And again, we did do quite a bit of Raman imaging at one stage. We never published anything on it. It's okay. It's not particularly, the resolution's still not great, but you can see things, discriminate things based on Raman bands. Basically, you say you're looking for quartz, so you look for the band at, well, you're looking for coesite, say, and it's the bands at 520 for the main Raman band. A1 band for coesite is at 520. So that's what you map out. And again, there are different ways of doing it. And I would suggest to anybody to make sure you get everything set up properly for what you're looking at. Don't just assume the instrument's doing the right thing. You got to play. There's nothing wrong with going and fiddling with instruments and adjusting things. Yeah. That if you're allowed to adjust them until you get good spectra.
Have you ever changed your mind with a specific explanation that you came up with in your early career, and later on you learned that okay, there might be another possible explanation? Is there anything in your research work, something like that?
Yeah, just recently.
So what's the study?
So okay, so in 1991, I'd been sitting on. I got interested in sodium germanates because of a phenomenon called the germanate anomaly, which is this maximum in density. Mm-hmm. And people had always said, well, the original model was that this density maximum occurred because there was a coordination change of germanium from 4 to 6, and there were no non-bridging oxygens formed, which there should be, right? And so the structure densified. And in the 80s, I realized that this was not the explanation for the germanate anomaly. And I sat on this paper for probably almost 5 years. And then I sent it in to be published. And it caused a big kerfuffle with everybody that worked on germinate glasses because I gave a completely different explanation. And recently, I've come back to start looking at the germinate anomaly. Well, right now, we're very interested. You know, you have this idea that you have based on Zachariason's paper from 1932. And this idea of modifiers and formers, and the silicate part of the formers, and the modifiers break bridging oxygens to generate non-bridging oxygen and sit in the rings in the glass. This concept is still the commonest explanation for everything, but it's from 1932, people. Things have changed, okay?
Yeah.
So one of the things we've been looking at is where does sodium go in a glass? So everybody will tell you, oh, it breaks the bridging oxygen to form non-bridging oxygens, and then it sort of bonds to the non-bridging oxygen and sits in rings or whatever. And so, and you have all these people that do these MD simulations and things like that. And one of the problems with the MD simulations is they never actually analyze their data. They spew out bond lengths and bond angles, but they know where all the atoms are in their simulation. Why don't you tell us, where does the sodium bond to? Is it doing what you think it's doing? Because they don't actually say that. And so we have been looking at where does sodium go when you mix it with silica. And we've done a whole series of molecular orbital simulations of various sodium silicate structures. And we're in the process of writing all this up, but it should turn everything upside down in their world of glass science, because what they think's going on is not going on. Other things are going on which they have completely ignored. And I'm not going to get into the details, but what it brought me to was I got invited to go to non-crystalline materials 15 last year at Cambridge. It was at Cambridge. And so I got up to give a talk, and I thought, I'll talk about the germinate anomaly, because a lot of what we're talking about, or what we've found with sodium, is what's, I think, causing the density behavior in the germinate anomaly. Now, every time I talk in 2007, I gave a talk on the germinate anomaly at NCM 7 or 8 or something in Prague, and caused a bit of a problem, or a bit of a fuss. And then, so at Cambridge, I went through, in Prague, I'd listed all the things that were completely inconsistent with a mechanism involving a coordination change. And then in 2011, I showed that the non-bridging oxygen vibrations, the Q2 and Q3 vibrations, they are there right from the minute you add sodium, but their intensities are very weak. And there has to be a reason for that. But they are there, and they never shift position. As you add more sodium, those peaks become the biggest Raman peaks. So at 30 mole% sodium, they're the big peaks at the high frequency. And they come from this exact same position at 5 mole%, okay, and below. But the community's entrenched in this idea of coordination changes. You know, something happens, there's a coordination change. And my question is always, what causes the coordination change? Something has to drive it, right?
Yeah.
And it's that something, I believe, is driving the germinate anomaly. And my original paper was that it was small ring formation that was driving the anomaly. And that's still partially true. And the coordination change is responsible for the high alkali, the decline in the density. And the bit that triggers off the coordination change and the formation of small rings, that's the thing that needs answering. So we have some idea as to what's doing that. And sometimes, I'm amazed at what people don't investigate. So we took a look at all the density data, and we looked at the partial molar volume of the alkali and the GO2. And what you see right at the beginning for the first few, 5, 10, 15 mole percent is that it's not the GO2 that's driving the changes, it's the alkali. There are massive changes in the partial molar volume of sodium, Na2O, which means there's something going on with the Na2O, which is what we're seeing with our simulations. And so the explanation, and I haven't written this up because, to be honest, I kind of fed up with trying to get these people to change their minds about things. But the thing that drives the anomaly, the three small rings are still important. But what's actually triggering it off and driving it at low alkali content is nothing to do with small ring formation or the coordination change. We've recently put out a lot of papers in Geology on density and partial molar volume in magmas. And what is happening is something called electrostriction. So what happens is when you put the alkali in, there's a collapse of the oxygens around the GO4 tetrahedron or the SaO4 tetrahedron toward the alkali. And so that it causes a sort of collapse of the rings and a compression, which is the trigger for the coordination change and the reason why the density goes up initially. And that's relatively recent for change from what I originally said about that. And it's happened a few times. I mean, I'm not one to get entrenched in an idea I suggest. I'm quite happy if you say I'm wrong. Mm-hmm. Great. Yeah. Come and one of the things, I'm a great believer in communicating with people. Don't be afraid to email them. If I don't agree with you, that's fine. That doesn't mean you're my enemy. I'm not going to refuse to let your paper be published. Mm-hmm. And like Bjorn Meesen, who's a very well-known guy on glasses in geology, Bjorn and I don't see eye to eye on anything to do with glasses. All right. He's retired, of course, now. And I have a lot of respect for him because he's been a prolific producer of work on magmas and melts in geology. And so whenever we're at a meeting together, we get on really, really well, despite the fact we'll contradict each other in the talks. But we'll have breakfast together, we'll go out for dinner together, we chat about things. And the funniest thing was when I met him and the first time, I'd never met him. And I was standing at a bus stop it was a geology meeting in Pisa in Italy. And this car pulls up and it's Bjorn Meesen. And he opens the door and I'd just been introduced to him at breakfast. And he said, "Grant, do you want a lift to the conference?" And I said, "Oh, okay." And as I got in the car, he looked at me and he said, "I guess we shouldn't talk about melt structure, though." And I said, "No, probably not a good idea," because we totally disagreed. But very nice guy. And, and if I disagree with somebody, I'm not going to block their paper. But this happens all the time, of course. If you say anything different, I had this problem just recently with a paper. And you get papers they give a very one-line response as a review. And that's not a review. If you want to criticize me, write out why you're criticizing me. Explain it to me. But a lot of people just say, "No, I don't believe this, reject it." And that's so frustrating. And so recently, I've been trying for the last 3 years to get a paper on Raman spectra of silica out. I finally have it coming out now, but it's taken 3 years because people simply don't want to believe it, even though, their understanding is based on some sort of theoretical calculation, and mine's based more on experimental data.
Mhm.
And, you get these people that do this, one-liners. When I was doing atmospheric stuff and the Antarctic ozone hole was so popular, we sent a paper in on something, and I got a one-line review. I don't believe this, reject it. So I wrote to the editor and said, this is not a review. Could you please have this reviewed properly? So he sent it back to the same person, and it came back with 2 lines. I don't believe this, and I don't think it should be published, or something like that. So then we got a hold of the editor, and I just said to the editor, do your job. Your job as an editor is to get this paper reviewed, not some snide comment by some anonymous person.
Yeah.
And there are too many people out there that reject papers because they don't believe it. If you can justify to me what you're saying in your paper, even though I don't agree with you, and I could and I'll certainly write back and say I don't agree with you, and you should read all these papers and such and such and such and such. But I'm not going to can it because I disagree with you, unless you've done something really, really dozy,
I see.
So anyway.
Yeah, that's again one of my big questions always when you are applying. When you are applying for a grant, someone is deciding that. It's peer reviewed, right?
Yeah.
Someone else is deciding in the community that you should do this or not. Or in the case of an article, a research work, I think, yeah, someone else again, they decide that whether it's worth publishing or not. So it's a big question for me, which approach is correct, at least in terms of papers. Should it be published? And then the community, the researchers in the community, they decide to use it or not. Or sometimes I think that uh, even an idea, maybe it's, let's say, wrong or something controversial, at least it initiates thinking from different angles.
Yeah.
So yeah, I in this part I agree with you that we cannot simply block papers, different views, because we think that it's incorrect. Uh, okay, thanks for the explanations and all these things for this part. Um, let's go to the next part beyond the lab. Uh, I would love to also ask a few questions about the personal aspect of your life. So, what do you do in your spare time?
Well, I spend almost 6 months in New Zealand and 6 months in Canada. And my country of residence is Canada.
Mm-hmm.
And I have a cottage it's a cottage on a lake about northwest of Bancroft and east of Algonquin Park. And when I'm in Canada, I play golf a lot.
Mm-hmm.
I do a lot of little renovation things around the place while I still can. I can still move about. And I have a kayak. I like to kayak around the lake on Saturday mornings and things, do something like that. Then when I'm here in New Zealand, about just a year or two before COVID started, I bought a house here.
Mm-hmm.
And I spend almost 6 months here. I can't without becoming a tax resident, which I don't want to be, because then they'll tax. There are tax reasons. Let's put it that way. So I bought this house, and when I'm here, I play tennis a lot. I've played tennis since I was 10. I really enjoy playing tennis, and not so much this year, but previous years, I like to go fishing a lot out on the ocean. So I go fishing. I have a cousin. I have very few relatives, but I have 3 cousins live in this area.
Mm-hmm.
And my grandparents used to live. So I'm on a ridge, but this house backs into the bush, the native bush. And on the other side of the road, everybody has a spectacular view of the ocean, because I'm in an area that's it's a big tourist spot in New Zealand, and you have all these islands, out, and the ocean is right there. And it takes me 5 minutes to go down to the beach to go for a swim. Okay. I have a motorbike. We periodically do little trips around the country at different places. I like camping, going to campground.
What was your dream job when you were a kid?
Okay. So when I was about 10 or 11, I knew I wanted to do a PhD in virology, viruses.
Yeah.
And I went to the University of Auckland with the express intent of doing that, because there was a very well-known virologist at the University of Auckland at the time, worldwide. He was well-known worldwide for his work on various types of viruses. But as I said, I got put off by the biology courses and botany and zoology and stuff like that. And I always thought my best subject at high school was biology. It turns out it was math. I didn't realize that when I look back at some of my old grades, right? I wanted to be a virologist. It didn't turn out that way. So there you go.
Yeah, I see. So if there were another world, a parallel world, you could choose another job, different job, which one you would rather pick?
Well, I'd have to be doing research, because I love doing research, okay? Yeah. And the aspect of research I actually like, and this will sound really bad, is I love disrupting the accepted explanation of things by pointing out things that contradict the model that people commonly believe is correct. And so I kind of like doing that. So it would be doing research at anything. I guess at one point, I kind of regretted not going into chemistry more, or I would be quite happy working in any field except theoretical mathematics, which would drive me nuts. But so, yeah, just doing research. So, as the last question, do you have any regret? Going into glasses and stuff like that? No. No. I mean, in your career, have you decided? I mean, do you have any? Yeah. Okay. Yeah. So I very much regret not applying to MIT. Do I have any regrets? Not really. I am not like. I don't really promote myself, okay, at what I do. Like, I'm not out there trying to get in front of everyone. I don't like any of that stuff. I don't even like doing this interview with you in that sense, okay? Which is why I turned you down the first time. But these days you got to be sort of a self-promoter as well, and that's just not me. And I don't regret not doing that generally, but the regret is that to some extent, I think I could have had a bigger impact on stuff if I had have done that. Not in Canada, but internationally, because I do everything internationally. I don't go to Canadian meetings anymore. I go to, I like international glass meetings, particularly the smaller ones with about 200 people, 250 people. And I'd say I'm quite well known in the glass community, but not in Canada. Regrets? No, not really.
Mm-hmm.
I think I regret not retiring earlier.
So, one more question. If there were a time machine, would you rather go 100 years back or 100 years forward?
I think backwards. I don't like the look of the future. Partly, maybe it's because I'm getting older, but I don't have any social media. I have no interest. I find Google has become so intrusive. I want to get rid of it off my phone. So I'm going to now look for a phone that doesn't have Google associated with it because it's an Android phone. And as for AI, I think it's grossly overrated for what it is. I asked on Samsung phones, you can't get rid of Meta AI. Okay, it's the AI. So I told it to delete itself, and it said it can't do that. So then I said, well, don't ever talk to me. That worked. It doesn't talk to me about anything. Okay. Even the students now use Chat GPT to write things, right? Yeah. So now the students are not learning how to write. They're clueless as to grammar. And they spew out these Chat GPT things. And the worst thing is you can tell it's a Chat GPT produced essay or thesis because there's no personality to the writing. See, I think it's very important that students and people, when you write something, you develop a writing style and there's a personality to it. Mm-hmm. And people can read your papers without knowing who wrote it and recognize, oh, this was written by such and such. Mm-hmm. And so I don't look forward to any of that. I don't look forward to all of the politics. I don't like the way some things are gone, I guess, in research. Mm-hmm. So I'm quite happy. I'd rather go back in time, I think. Yeah. So it'd be more to the time when you really had to think about a problem. Yeah. Not rely on machines or computers.
So thank you, Professor. Thank you so much for sparing your time and agreeing doing this interview. And have a good day.
All right. Have fun.